Here we go, folks. Section 10.4 and 10.5 kind of combined. And to introduce what we'll be doing in these sections, we need to kind of review a little bit. So, can anyone tell me what the sum of this series is? Can you tell me what the sum of that series is? I don't know. I would not be able to take your answer in that form, because I do not know. Andrew?
Sum n equals 0 with n on top and 0 on top. 1 times to the n over.
Okay, yes, indeed. Can you tell me what that sum equals?
Oh, 1 over.
Okay, can you tell me what the sum of this series is? Can you tell me the sum of that series? No? So you're getting closer now, you're thinking in the right direction. It's e to the x. So when I ask you for the sum of the series, that's what the series converges to. So this series represents e to the x because if I add them all up, it's going to equal e to the x. So what does this series equal?
Oh, e to the point 1.
E to the point 1. Right? So when we keep talking about these series and whether or not they converge or diverge, well, if they converge, then they have a sum. Their sum is some value. If they diverge, they do not have a sum. You just keep adding more to it all the time. Okay? So what we are doing in sections 10.4 and 10.5 is deciding if all these different series that we are going to be looking at, deciding if they have a sum or they do not have a sum. So we are going to come up with some tests. We'll be using some tests that allow us to determine if a series converges or diverges. Okay? If it has a finite sum or not. Now, most of the time, we cannot tell what the sum is on the function. We only know for the Maclaurin series, that table of series that we have, those are given to us because there's some work done on those, excuse me, where they've actually looked at the value of the error. Excuse me, sorry. So, the reason we can say the sum of all of those are either 0.1 or cosine of whatever. Just a minute. So, the reason that we know that those actually sum to the function is because mathematicians have done a great deal of work looking at the error between that series and the true function. And they have found that the error is 0 as n goes to infinity. So without that error analysis, we wouldn't be able to say that these sum to e to the x either. It's very difficult for us with our current status of ability to be able to find out what the sum is, unless it is one type of series, geometric. That one we know how to find the sum of, right? That's our favorite one. All right, so our focus in 10.4 and 10.5 is testing series to find out if they do converge or they don't converge. They add to a finite sum or not. And let's start with just getting some terminology straight on where we're going. So if I have a function that looks like that, and I have a series that I am using to model it, and the series comes in like this, and then goes off like that. What do I call this region from about here to here? That's our interval of convergence. Okay. And just so we are aware, ooh, that looks like an M, but it's an M. Just so we are aware, we'll be referencing the radius of convergence a lot in this chapter, and the radius of convergence is half of the interval of convergence. There we go. All right. So if my interval of convergence was x is between 6 and -6, then my radius of convergence would equal what? 6. Half that distance. Okay? All right. And when we're dealing with a power series, there's 3 possibilities of what could happen when we're interested in convergence or divergence. The first is that our radius of convergence is equal to 0. So if our radius of convergence is 0, what does that say about the series? It does not converge at all. It diverges. Sometimes they say it converges just at one point, which is not very helpful. And diverges everywhere else. Wow. But that is a case where you would tell me it is divergent. Okay? All right. The second situation that can happen is our radius of convergence could be infinite. What would happen then? It's the exact same as the function. It converges for all x. Yes. We know sin x has an interval convergence that's for all real numbers. So that is the case. Oh, that's great. There. All right. And then the third thing that can happen is that our r could be less than infinite, but greater than 0. And that's when we have an interval of convergence, like the picture we have above. All right, and when this happens, we need to test the endpoints of the interval to see if they are included in the interval of convergence. So we need to test the endpoints to see if they're included in the interval. Okay? So these are the 3 possibilities that can happen. As we go through, I'm about to show you a great number of convergence tests. And as we go through them, one of these things is going to happen each time. Okay? All right. So let's move on. Flip your page over, and so the next 2 pages are your list of tests. And I need you to add one more above integral test, and it's one that we have actually already talked about, and it is the nth term test. And we talked about this already. This is the limit as n goes to infinity of the definition of the series, a sub n. If that does not equal 0, then what do I know? The series diverges. can I say, if it does equal 0, then it is convergence? No, thank you. Please don't ever say it. Don't ever say it. This only tells us about divergence. It does not tell us about convergence. We can have lots of series whose limit is 0, and they still diverge. All right, so this only tells us about divergence. All right, our first test is the integral test. Well, in calculus, an integral is an infinite sum, isn't it? Okay, right? Yes. Okay, good. So, I can model a series with an integral. And if the integral converges, then the series converges. And if the integral diverges, then the series diverges. The way that we can model it, though, is we let our n, or our k in this case, go out to infinity. We're interested in what's happening as we go way out there. So, underline in your notes that this function has to be continuous, positive, and decreasing. As we go through each of these tests, I'm going to give you the conditions that have to apply to use them, and other little helpful hints about when you might want to. Nobody's moving, so they shut up. Okay. Anyway, so on each of the tests, I will be giving you when this test might be helpful and the conditions that have to apply to use this test. So these are the conditions: continuous, positive, and decreasing. Now, also for each test, you'll have one or two examples. So this is example 1, and this is for the integral test.
Wait, could you go back to this?
Yep. You have it in front of you too.
Oh, okay.
Yeah. Because I was like, I didn't write anything this time. I think. Okay. So I'm going to use the integral test to determine the convergence or divergence of our two building blocks, our two series that are helpful in many other series. And the first is the sum from n equals 1 to infinity of 1 over n. So on this interval, is the function continuous? Yep. Is it positive? Are all the values positive? And are they decreasing in absolute values? Indeed. So we can use the integral test. We will do an integral from 1 to infinity of 1 over x dx. And if this integral converges, then this series converges. What do I need to do when I have an infinite upper limit? We need a limit as p or a, whatever you want to call it, goes to infinity of the integral from 1 to p of 1 over x dx. Now we can carry on with our integral. The antiderivative is natural log of the absolute value of x. We don't really need the absolute value this time because we're all positive. To be evaluated between 1 and p, and we have our limit out in front as p goes to infinity. Now we evaluate the limit as p goes to infinity of natural log of p minus natural log of 1. And what happens? It goes to infinity. This one diverges. So this series diverges. Done. So from here on out, it will be greatly to your benefit to know that 1 over n diverges. Okay? And now the second one we need to figure out is... I sure can. We're going to do another integral test example. And for this one, it's the sum from n equals 1 to infinity of 1 over n squared. Process is the same. Is it continuous in the interval? Yep. That's a check mark. Yes. Are they all positive? Yep. And is it decreasing in absolute value? Done. So we can now set up our integral. I'll go ahead and step ahead to the limit as p p goes to infinity from 1 to p of 1 over x squared dx. The antiderivative is negative 1 over x my limit in front, limit as p goes to infinity of negative 1 over x, evaluated between 1 and p, and what happens on this one? Louder? Careful. Watch your negative. Yes, thank you. Because the limit as p goes to infinity, negative 1 over p approaches what? What does this one approach? 0 plus 1. The integral converges, which means that the series converges. Done. Okay? So now we know 1 over n diverges, 1 over n squared converges. Very useful series for other tests. Any questions? I won't be getting 1 and 2.
So it doesn't converge to 1?
We don't know that.
Okay.
Yep, we can't say that. We can say that it converges, but we cannot say that it converges to 1. All right. So let's go back. Our next test is the comparison test. So I said for integral test it has to be continuous, positive, and decreasing. For the comparison test, the functions must be positive. And this is usually helpful if you want to compare to a geometric. It makes it pretty easy. If it doesn't compare well to a geometric, then you might want to try a different test, because you need to be certain about what you're doing when you use this one. All right, so let's read it. It says, suppose that we have two series, a sub n and b sub n, and they're both positive, and a sub n is less than b sub n everywhere. So each term in a sub n is less than each term in b sub n everywhere. If b sub n converges, then a sub n converges, and if a sub n diverges, then b sub n diverges. So let me give you some pictures to help you understand what's going on here. This is example 2 for the comparison test. So I want you to consider a series that looks like this, and one that looks like this. We're going to call the closed dot a sub n and the open dot b sub n. So if a sub n diverges, what happens to b sub n? Also diverges. So if b sub n is bigger than a sub n for every single term, and we know that a sub n diverges, then b sub n must also diverge. Correct? So that's the comparison that we make here. So if a sub n diverges, so does b sub n. All right, and then the second part of this said, if I have one that looks like this, remember they have to stay positive, can't go negative, and now I have this. So now, closed dot is a sub n, open dot is b sub n. Let's say I know that b sub n converges. And what happens to a sub n? It's like the sandwich here. It's getting squished in between the x-axis and the converging series. So a sub n must also converge. Okay, does that make sense with the pictures, what it's doing? It's like each one is pushing the other one to either diverge or converge. Sam?
So for the bottom one, if you had A sub, you might just use the field discount to correct.
Correct.
If you had A sub converges on the bottom one, on the second graph, you wouldn't be able to tell whether the extent does or not.
That's correct. Yes. So now let me show you how this is useful. Let's say I want to know, does the sum from n equals 1 to infinity of 1 over 4 to the n and then plus 1 converge or diverge? That's the question. And I want to use the comparison test. So I am going to compare that series to one that's very easy to work with and that would be related to this, 1 over 4 to the n. So let's write out a few terms of this series. What would they be? 1 fourth plus 1 16th plus 1 64th plus 1 256, and so on. All right, now let's compare that to this one. 1 over 4 to the n plus 1. What would that one be? 1/5 plus 1/17 plus 1/55 plus 1 over 257, and so on. All right, so looking at the top one, what kind of series is this? It is geometric with a common ratio of 1/4, so that means that it does what? Converges. And how do each of the terms in the series we're interested in compare to the terms in the geometric one?
You add one to the bottom.
They add one to the bottom. Are they slightly bigger or slightly smaller? Slightly smaller. So I have a convergent geometric where every term is larger than the terms in my series that I'm trying to figure out. So I have this situation. The geometric is the open dot. The series we're trying to figure out is the closed dot. And our geometric converges, so what does that say about the series we're trying to figure out? It also converges. So this series converges by the comparison test. And that's the type of answer I want to see. I would like to see converges by what test? And I will need to see work like this along with it, and then the statement at the end. Okay? Questions on that one? Yeah, Lauren.
Did you just come up with 1 over 4n, or is that given to you in the problem?
It is not given to you in the problem.
Okay.
So that's why on the front I said compare to geometric test, or compare to geometric series quite often, because geometric series are so easy to work with.
Okay.
So I found a geometric series that was pretty closely related to it. Okay? You need to be certain that your function that you're using stays below the geometric always, or stays above the geometric always, to make this decision. So unless you're certain, I say use a different test. Okay? All right. Questions on that one? Andrew, are you with me? Indeed. All right. Okay. The third test is the limit comparison test, probably your most useful test for tonight's homework. And I tend to use this one a lot. I find it easy to work with. In this one, we have two series, and they're all positive. So there's the condition. And what we do is we set up a limit of one series over the other, and then based on how that limit comes out, we can draw some conclusions. And n, it's a sub n over b sub n, and then goes to infinity. All right. So this one, when is it useful? When we have all n's in the series. when we don't have x's. Sometimes we'll have x's and n's. If it's just all n's, or all one variable, that's when this one is useful. All right, so let me go write some clarifying notes for that. This would be example 3 for the limit comparison test. All right, the way it works is we set up a limit as n goes to infinity of a series we're trying to figure out. So this is the one we're trying to figure out. Over b sub n, which is a series that we know what happens. And the most useful ones, 1 over n and 1 over n squared. Two we figured out at the beginning of this lesson. Okay? All right. So we will take a series that we're trying to figure out, put it over a series that we know. If the limit equals a constant that does not equal 0 or infinity, then both series do the same thing. If the limit comes out to be 0 and the bottom converges, then they both converge. And then if the limit comes out to be infinite and the bottom diverges, I need to make sure to get my and in there. Then they both diverge. All right, sounds like a lot of information, but as you work with this, it becomes very easy to deal with. So let me show you an example to start. And let's see, let me see what I chose. N over n plus 1. So we want to know if n over n plus 1 converges or diverges. This is the sum from n equals 1 to infinity of n over n plus 1, converge or diverge. That's what we're figuring out. So we set up our limit. Limit as n goes to infinity. The one on top is the one we're trying to figure out, n over n plus 1. The one in the bottom is one that we know about already. And I usually just start with 1 over n. And I evaluate the limit. So this comes out to be the limit as n approaches infinity of, what, n squared over n plus 1? And what will that limit approach? Infinity. So we are at this condition here. The limit approaches infinity. So if the limit approaches infinity and b sub n diverges, well, does our b sub n diverge? Yes, it does. Then both series diverge. So both diverge. And that tells us that the sum from n equals 1 to infinity of n over n plus 1 diverges. Okay? What would have happened if that limit came out to be 0? Well, if the limit comes out to be 0 and b sub n converges, but the one that we used did not converge, so you couldn't draw a conclusion. But what you could do is quickly switch to put 1 over n squared in the bottom and see if it still comes out to be 0. And then you can say that they both converge. Okay, so let's try one more example. And this one is n squared plus 1 over 2 to the n. We are finding out if the sum from n equals 1 to infinity of n squared plus 1 over 2 to the n converges or diverges. All right, so we get our limit as n goes to infinity of the one we're figuring out, n squared plus 1 over 2 to the n over 1 over n. And this comes out to be the limit as n goes to infinity. Oh dear. No, that's right. Of, what do we get? N cubed plus n over 2 to the n. Well, what is that going to approach? 0. 2 to the n is going to grow faster than n cubed. That's going to approach 0. Well, if it approaches 0 and the bottom series converges, then they both converge. Does my bottom series converge? It does not. So this is what I meant when I said, well, now I can quickly make a change. Limit as n goes to infinity of n squared plus 1 over 2 to the n over 1 over n squared, and see if it still goes to 0. And here we get n to the 4th plus n squared over 2 to the n. What will that one go to?
No.
Sorry?
Also 0.
Also 0. So now, the limit goes to 0 and my b sub n converges, so they both converge. Okay? So we've looked at the second and third conditions that can happen. If it comes out to be 0 or it comes out to be infinity. If it comes out to be a number, then they both do the same thing. Okay? Questions on limit comparison? Okay. What time am I at? Our next series. Come on back, come on back. The next series, the next two series, harmonic and P series. Not a lot of work involved, but you need to recognize them. So a harmonic series is a series whose reciprocals form an arithmetic series.
All right.
So the basic one is 1 plus 1/2 plus 1/3 plus 1/4. Right? If I take the reciprocals, it's an arithmetic series with a common difference of 1. Harmonic series, if you identify it, then you can say the series diverges because all harmonic series diverge. Okay? The basic one that we already proved was 1 over n. We proved it with the integral test, and we showed that it diverged. All right? So harmonic series will diverge, but nothing can ever be that simple. If we have an alternating harmonic, which means that the signs change on every term, like 1 minus 1/2 plus 1/3 minus 1/4, and so on, alternating harmonics converge. Yep. We can prove that with the alternating series test, which we'll show a little later. So, if you have a series, and it is one of these, the harmonic or the alternating harmonic, or what we're about to discuss, the P series, you can just say it converges because it is one of those. All right? The P series, this 1 over n is also the basic P series. The P series, as you see in here, is the sum from n equals 1 to infinity of 1 over n to the p. It does not have to start with 1. So some examples of P series would be the sum from n equals 3 to infinity of 1 over n cubed. or the sum from n equals 10 to infinity of 1 over n squared. Those are all p-series.
Does that start at n equals 1?
The first one did.
Yeah, okay.
But they don't have to.
Okay.
So that's why I'm giving examples that start elsewhere. All right. And with the p-series, we actually proved the first two p-series. We did 1 over n, and that one did what? Diverged. And we did 1 over n squared, and that one converged. And if we had looked at 1 over n cubed, we would have seen that that also converges. So our rule for a p-series is, if p is less than 1, less than or equal to 1, it will diverge. If p is greater than 1, it's not. No, it's not.
I mixed up my show.
Okay. If p is greater than 1, then it will converge, like 1 over x squared and 1 over x cubed and so on. So if in your process of solving a problem you run across a simple one like that, you can say it converges or diverges because it is a p-series with a p greater than or less than 1. Okay? So we hope to see those. All right, moving on. Our next test is the alternating series test. So let's read it first, and let's look at the conditions. Slide, please. All right, suppose that we have a series a sub n, and either a sub n equals negative 1 to the n b sub n, or a sub n equals negative 1 to the n plus 1 b sub n, where b sub n is always greater than 0 for all x. Then if these three, it's actually three conditions, I'm going to have you add one. If these three conditions hold, then the alternating series converges. The first one we'll call A. And the way I state it, basically what they set up here, but I like to say it more clearly, in my opinion. I need for this series to be strictly alternating, which means plus, minus, or minus, plus, not minus, plus, and so on. Has to strictly alternate on every term. The second condition is the limit of a sub n has to go to 0, and the third is that the terms must be decreasing in absolute value. Okay? To show that it's decreasing in absolute value, you must show that the n plus 1th term will always be less than the nth term. If those three things happen, then the series converges. So let's go do our example. This is, I don't know, example 4, not sure. But it's for alternating series. And the one I chose was the sum from n equals 2 to infinity of negative 1 to the n plus 1 times 1 over natural log of n. All right, so each time I say, when do we use this? Well, if you have a series that has a negative 1 to the n, or a negative 1 to the n plus 1 in front, then you could try the alternating series there. Okay? All right, so the three conditions. Would this be strictly alternating? It would, because the natural log of n, as n gets cubed, stays positive, right? And the negative 1 to the n plus 1 would make each term change sign. So it is strictly alternating. Is the limit of the absolute value of a sub n as n approaches infinity equal to 0? We ignore the alternating. Is the limit of this going to 0 as n gets big? It is indeed. And third, is it decreasing? Is a sub n plus 1 always going to be less than a sub n? Well, this one you have to show me a little work on. You have to, and again, we're only interested in the part that does not include the negative 1. So we need to think about 1 over the natural log of n plus 1. Will that always be less than 1 over the natural log of n? It will, so we need to show a little bit more, and what we can show is that the natural log of n plus 1 is always greater than the natural log of n, correct? As we move further to the right, the y value is going to be higher for the n plus 1 term. Well, if this is greater than that, then 1 over the natural log of n plus 1 will be less than 1 over the natural log of n. So this shows that we are decreasing in absolute value. Yes.
Can you write that in words?
You can. Yep, you can write it in words. So now, if the three conditions hold, then we are done. This series converges. Done. Questions on alternating series? All right, almost there. Couple of things we just need to discuss. Definition: a series A sub n is called absolutely convergent if, when I put absolute value around the A sub n definition and check for convergence, the series still converges. That's called absolutely convergent. If the series converges without absolute value, but diverges when we have absolute value, it is called conditionally convergent. Okay, we just need to know those terms because sometimes you'll be asked to find out if a series is conditionally convergent, absolutely convergent, or divergent. So that's two things we really need to look at. Check to see if the series itself converges, check to see if the absolute value of the series converges, and then determine whether it's conditionally or absolutely convergent. All right, if a series is absolutely convergent, then it is also convergent. So when you're doing this, you should start by doing the absolute value one first, because if that's true, then the other is true also. Okay? All right. Finally, ratio test, our last one. So the ratio test, when do we use this? We use this first when there are factorials. The other times we would choose to use this is when we're asked to find an interval of convergence, or if we're asked to find a radius of convergence. Those are three situations where I go to the ratio test. For numbers 2 and 3, the interval and the radius of convergence, you have no other options. Ratio test is it, unless it is a geometric, which we already talked about how to find an interval of convergence for a geometric. Okay, so the way that the ratio test works is it kind of forces a situation like a geometric. It takes the n plus 1th term over the nth term, right here, and takes the absolute value and takes the limit. So it's the limit of the absolute value of the ratio, just like with a geometric. And if that limit comes out to be less than 1, just like a geometric, then the series converges. Greater than 1, the series diverges. And equal to 1, please note, equal to 1, it is inconclusive and you need another test. Okay, so let's go use this. And ratio test example, I think it's example 5. I don't know. And what I've chosen for this one is n plus 3. We want to know if this series converges or diverges from n equals 1 to infinity of n plus 3 factorial over 3 factorial, n factorial, 3 to the n. So I see those factorials, and I want to know, converge, that's the question. Does this converge? All right, I see those factorials, and that reminds me that ratio test is a useful one for that. So we set up our limit, L equals the limit as n goes to infinity of the absolute value of the n plus 1th term. That means I replace every n with n plus 1. So on top I have what? N plus 4 factorial over 3 factorial, n plus 1 factorial, 3 to the n plus 1. All of that over the nth term, which is what is above, n plus 3 factorial over 3 factorial, n factorial, 3 to the n. All right, here is my warning. Be neat and tidy. These involve a lot of keeping track of everything. Be organized in your work, because they always pair up nicely and nice things happen in our canceling. But if you're a mess, you're going to miss something. Okay, so be neat and tidy when you do this. So down below, here we go. We're going to rearrange it so it's easy to see how things cancel. We're going to do the limit as n approaches infinity of the absolute value. So when I divide by this fraction, it's the same as multiplying by its reciprocal. So I can put the n plus 4 factorial over the n plus 3 factorial. Times. Now these things that are in the denominator here, when I multiply by the reciprocal, will come to the top. So I'll have a 3 factorial over a 3 factorial. That takes care of that and that. I will have an n factorial over the n plus 1 factorial. And I will have a 3 to the n over 3 to the n plus 1.
These are all multiplied, correct?
Yes, yes. Because everything in there is multiplication, so we're just rearranging things. So now we need to think a little bit. What is n plus 4 factorial, which is n plus 4 times n plus 3 times n plus 2, and keep going, over n plus 3 factorial. Yep, we get n plus 3 times n plus 2, and so on. So everything here and here cancel, and we have n plus 4. 3 factorial over 3 factorial? Lovely, 1. What am I going to get when I have n factorial over n plus 1 factorial? 1 over n plus 1. So I will warn you, be careful about managing your factorials, because sometimes we end up with things like 2n plus 2 factorial. So just be careful. And finally, this ends up being what? 1 over 3. That is 3 to the n minus n plus 1, which gives us 3 to the negative 1, which is 1 over 3. And we're still taking the limit as n goes to infinity. One final rearrange, which may not be necessary for you, but I'm going to show it anyway. Limit, I'm going to put the n plus 4 over the n plus 1 times 1/3. And what does that limit go to? The limit itself on the n's goes to 1. So we are left with our limit equaling 1/3, the absolute value 1/3, which is 1/3. And how does that relate to 1? It is less than 1, so what does that say? It is absolutely convergent. Yay! Done. All right. Now, I'm going to save the interval of convergence example for tomorrow. That's all I'm going to talk about tomorrow. We'll do one example like that. So, I am done with you for today. And that. There is a change in the homework for tonight. You're doing page 515. Page 515, and I'm combining the 2 days homework. Remember it, I'll check it on Monday. And you're doing 3 through 43. Watch my writing. A-L-L. Not odd. All. 3 through 43 all. What I suggest you do for tonight, so you stay ahead on this, is I suggest you work on the 29 through 43 section tonight. After I do the interval of convergence example tomorrow, then you can work on the earlier part as well. Okay?
So, you said it's not due till Monday?
Not due till Monday.
Yeah.